Okay, this is an incredible group. I was going to start, as you know, with a question around what's your definition of world model. We will not do that because that's the next 20 minutes of individual definitions. Maybe if we have time at the end, we'll come back to that for a set. But I figured we'd just dig right in into some of the meatier topics. I listened to all of the chats today, and I picked out a few where I figured there might be some, perhaps not disagreement, but slightly different stances. So I figured we'll just have a discussion. This is not one of those, here's the question, let's go down the path. I can't stand that, God. So let's start with physics. Anastasios, in your chat, your thesis was just by generating video, you can generate inside the model an inherent understanding of physics, and you showed us some videos. Why do you believe that? And then as you think through that, I'd love for anyone else on the panel who's got a contra view to weigh in as well.
Yeah, so I think that's mainly an empirical conclusion from just scaling those models and measuring how well they perform on different physics-related tasks. In general, our approach has been, if you want to introduce inductive biases to make sure that the model learns something well, introduce those inductive biases in the data that you're training on. Don't introduce them in the architecture. So we have very intentionally, tried to learn everything directly from pixels and not introduce any kind of 3D based priors. And we've seen that work pretty well. Like at some level of scale, you get pretty good geometric consistency. That's something you can also measure quite well. And so I don't think there is a fundamental reason in my mind why that won't continue scaling.
Someone has to take the other side of this. Is it true? Like just generate video and you get spatial knowledge inside suddenly a model and becomes a world model?
So I know that, Guru, you said you don't want definitions of world model. Let me still have one, and then I can ground the discussion. So for my definition, it is a model that predicts the next sensory state, conditional actions. Now, I think video is convenient. In fact, video is one of the sensors. It's called an RGB camera. But on a robotic system, you can have more than one RGB camera. And in fact, you have a lot more sensors. And I would say there are many modalities missing in today's discussion on world models. In addition to videos, there's tactile, there's force, there are the invisibles that we also need to put into these models to have a really holistic simulation, right? Holistic capture of how the dynamics should evolve. So I would say video is convenient. Video is easy to scale, it's readily abundant, but that's not the full story.
Okay. Sergey, you've done so many robots now that are actually in deployment. One of the few folks here who's closed the loop, along with Jim, on exactly what's happening in real life. What's your view?
I guess what I would say is that if you generate videos that people find compelling, I think it's very easy to get into a situation where you get a video that looks very good to people, but doesn't actually reflect a model's ability to simulate the kind of counterfactual effects of physics that you would care about. What that means is that when you give a model a prompt, it doesn't have to produce a prediction about what will happen to a real physical system in that situation if it does something. It just has to produce a result that to you looks like a good reflection of that prompt, which means that the model gets to choose. And that choice is actually very, very important. It gets to choose how to set everything up so that it looks good to you. Whereas if you need to actually plan and act in the real world, you need to handle the actual situation you're in, the actual plan that you're making, and whatever kind of counterfactual effect you might have. So what this actually comes down to, whether the model actually understands physics or not, as Anastasios alluded to, has to do with the data, of course. It's just that the data that we would use to get really great videos is not the data that we use to get counterfactuals. If you train a model on really good driving data, and then you ask it what happens if I drive into a building, it'll probably produce the building morphing into a beautiful road, and you're driving happily down the road. And people have actually done this, and that's exactly what happens.
Right.
So I think that the answer is yes, the model can handle physics, but you have to be very careful not to let it fool you.
Right, right. And while staying on this topic of what goes inside the model, I'd love a little bit of debate on. So we constantly hear, or we're certainly hearing now, and this I'll start with you, Jim. The era of VLAs is over, and the future is world action models. Do you hold this view, Jim? If so, why? And then I'd love for more panelists to weigh in. Is VLA, is it WAM, is it both? Or is VLA dead and it's all WAM going forward?
Absolutely, yeah. I know I talk a lot about word action models, WAMs, and VOAs. I think it depends on the level of abstraction that we work on, right? So there's the system 1 and system 2 thinking. System 1 is fast and reactive motor skills. System 2 is reasoning, right? Like, coding, tool calling, all of that. So I do think WAM is a very promising approach for system 1 because many of these physical common sense, right? Let's say, how do you grasp a cup? It's very difficult to break down and describe every frame through language tokens. It's just quite difficult from a first principle point of view. Now, regarding system 2, I would argue that Opus, GPTs, they are actually VOAs. These models are agentic. They take actions. I would argue these are VOAs, and in fact, more people use VOAs than they use WAM today because VOAs also serve other purposes. And that is the part where I discuss in my talk, right? Agentic scaling. I think that's going to play a big part, right? The VOAs, which are like the Opus and the GPTs of the world, they're able to understand the world through some perception and then calling tools and be able to help auto-research. So I don't see maybe one completely replacing the other, but it's really about the abstraction level that you operate on top of.
Right. Sergey?
I actually think that it's slightly the wrong question. Or, I mean, it's the right question for you to ask us, but it's maybe like slightly the wrong question for like a researcher to ask themselves, because it puts the model before the data in a way that maybe is not actually quite right. So the key to build a really good foundation model is to be able to productively ingest lots of very diverse data. And video data is one of those data sources, and it's a great data source. Now, most VLAs that are actually good, they are trained on video data, lots of video data. It's just they're trained on it in a web scale pre-training phase, which trains the understanding backbone. So I actually don't think that the right answer is to say like, oh, is it VLA or is it video? It's how do you use the most data? And then on top of that, there's some like kind of inductive bias, but as Ilya Sutskever used to say, inductive bias is trained data in disguise. So the effect of inductive bias might be large when you're testing things at a small scale, but it dissolves away once you scale things up. So really what we should do is say like, okay, we're going to leverage as many data sources as possible and then be pragmatic about what kind of outputs the model has to leverage them.
Right. Where you're, sorry, Mika, go ahead.
Yeah, maybe I can add like two points from our perspective. So the first one is, if you think about the tasks that we are working on, like racing and table tennis, I think language is actually not all that helpful. It doesn't really, you can describe how to do the skill, but there's very little information. I mean, in cognitive science, there's this classic distinction between declarative and procedural knowledge, right? So in order to ride a bike, you actually have to do it, and you have to learn the physics of it. The second one I would say is like, obviously vision, I think, is a great thing to condition on. At the same time, in some applications, you can't. So for instance, if we are in-game and we're shipping a game to a customer, and there's like 20 agents racing, we cannot render from 20 different viewpoints. There's just not enough compute, let's say, on PlayStation to do that, because most of the compute goes into rendering for the customer, like the player. And so I don't think, these are not sort of yes-no questions. They're sort of like, okay, what is the domain that you're interested in? What are you trying to solve? What's the application downstream? I will say that having large foundation models that can capture visual knowledge and language model is in many cases really, really helpful, but we also still need to distill the thing that we're actually interested in a particular moment and then maybe ship to a consumer.
No, I like that answer. It's not an either or. It really is use case dependent, and both have really sort of interesting applicability.
One more thing to add on the WAM versus VLA discussion is that generally there's a lot of convergence that's happening towards omni models that can actually predict both visual modalities, audio modalities, text modalities. And so ultimately it's kind of, to Sergey's point, it's all about like, what are you specializing the model during pre-training on? Are you specializing, is the data mix biased towards more low-level motion planning? Is it biased towards high-level reasoning? So it's less about it's less about WAM or VLA architecture. It's more about what are you dedicating the capacity of the model ultimately, and that tends to be the important factor.
Right. Backstage we were talking about robots and simulated data and stuff like that. Today, from what you're seeing, how much of real robot skill has to come from things like reinforcement learning in the physical world versus the digital world? And I'd love to then, this is one of those questions where I'm sure we all have a point of view. So I'd love to start with Wei and then maybe go down the line.
Yeah, definitely. So great question. So I want to separate that into different applications. On one side, for autonomous driving, so we care more about the behavior as well as the visual modality. And for those two, it's relatively easy for us to scale that up from the real-world data and inject that into the synthetic world with a more scalable way. And for that part, right now it's more like this. Many of the leading players for productionized end-to-end ADA system is mainly focusing on utilizing the real-world data, while some of the synthetic data can be utilized for the post-training stage. Well, we can see the trend that large-scale synthetic data can play the key role, and more important role, for making the autonomy to be more robust and safe. While on the robotics side, I think what I learned at this very point is that for tasks related to locomotion, for whole body tracking, so the reinforcement learning-based methods can be pretty useful and even dominate that. While for complex tasks like dexterous manipulation, it could be a bit hard for us to either create the high-fidelity synthetic world capturing many of the key physics attributes, or define a good reward function to really train the corresponding policy in closed loop. So at this very point, what I saw is that behavior cloning or imitation-based methods are still dominating.
Right. Let's fine-tune this question, Sergey, as we come down to you a little bit more. Let's say there are certain tasks you just have to do in that robot's embodiment, extreme precision in data collection versus simulation, egocentric data, videos, etc. What is that distribution? How much of one do you need and how much of the other? Are we still in the age where you just need to do the task over and over again 1,000,000 times? Or can you do a vast majority of the work either sort of in silico or through egocentric data, etc.? What are you seeing in real life now?
Well, I think there's two sides to that scale, to the scales there. There's the supply side and the demand side,
Yeah.
right? And this is where I think the future is going to be very different from the present, because in the present, I would say that in robotics, we're like in the bootstrap stage, where we're trying to figure out what would it take to get models for robots to be good enough so that they can actually be used with end-to-end learning. But we won't be in the bootstrap stage forever. Eventually, we'll be in the stage where there are as many robots deployed out there as there are vehicles on the road today, and there will be very plentiful sources of data from robots interacting with the world autonomously. And then reinforcement learning methods that can use that real-world data will be tremendously important. The other thing here is that the challenge increasingly as the imitation learning methods that you mentioned get better and better will actually be how do you bridge that last gap? How do you go from a 98% successful robotic policy to a 100% successful policy? And there, the domain gap is really important because you really want everything to line up to be absolutely ideal. So there, I think we will also need reinforcement learning in the real world. But I think that's what's coming in the future. I don't think that's the state today. I think your summary is an excellent summary of the state today.
Yeah. Jim, I know you've done some experimentation on this. What are you seeing?
Yeah, Guru, I think great scientists invent, greater scientists copy. I absolutely love to copy homework from LLMs. I look at them all the time. So what are the LLM folks doing? I think they are not just creating data anymore, they're creating environments. It's all about acquiring millions and millions of coding environments and then doing RO in those environments so that we can get the mythos and the GPT souls of today. That's how they got here. Not through imitation learning, eventually through reinforcement learning. So I see robotics to do something very similar, that we need to build environments. Then what are some options for environments? Right, option number one is you run RO in the real world. I think Sergey and Pi has done exceptional work over there. Absolutely important, right? The physics, perfect, because it's directly in the real world. And then option number two is classical simulators, right? Like Isaac Sim of the world. But those simulators, the bottleneck is not the simulation speed. In fact, the simulation runs very, very fast. But it's the assets, it's the environments, it's the tasks that we used to need a lot of artists to curate. But now there are recipes called Real-to-Sim that I believe is super promising to automatically scan the world and transport the real world into a classical simulator so you can both be data-driven while also relying on a classical fast physics solver. So that's option number two. And option 3, back to world model. I think one very practical use of video world model is to use that as a neural simulator. It's a data-driven, program-by-data neural simulator. Then it can take as input actions and then generate videos and sensor states, effectively using it as environment. But the thing is, it's going to run very slow, but it will have a huge amount of diversity, as much as the world model can afford. So ultimately, it's going to be reinforcement learning across these 3 options for robotics, using different types of compute, using different constraints. So I would love to see this as a more holistic approach.
Right. As we come up on time, I'm going to ask 2 sort of rapid-fire questions that I love. So first question, we'll start with you, Anastasis. The most amazing demo in robotics or world models you've seen recently, not from your company or team?
I've seen some great things internally, but yeah. One demo or one model release I really like was by, I believe it's a new startup called Induction Labs. The model is called Photon 1, and it's effectively a world model of based on screen recording, so a digital world model of sorts. And they show that you don't need, very often, like when you're training computer use models or you post-training LLMs to do well on computer use, you're leveraging a lot of kind of your text supervision in addition to kind of directly like screen frames from UIs or screens. But they trained a model entirely on essentially a video model on just screen recordings, and they were able to show that they actually get competitive performance with Gemini on computer use, or like Gemini, one of the small Gemini models, with an order of magnitude less compute. So I found that pretty impressive.
I think that says more about the nature of work we do on a screen than anything else. Jim, something that made you go, wow.
There's actually a robot that millions of people already buy and use on a daily basis. It's called Tesla FSD. I've been driving Tesla since last year, and honestly, I was amazed by the latest versions. And it's all like rush hours. You can see, right, the policy. It's able to negotiate super well in super crowded lanes, almost human-like, and I would say sometimes even better than I would have driven myself. So that gives me a lot of hope, because that is one physical system solving a very important task, autonomous driving. And once you spin that physical data flywheel, you get these huge performance gains, a quantum leap compared to a couple of years ago. So that's why in my talk today, I also stressed the importance of having data collection fade into the background. The data collection cannot be intrusive. And that's why when you have egocentric data on humans, you are able to capture this dexterity without interfering with what they're doing. And that's the way that we can draw a parallel with FSD and maybe someday get there for robotics.
I
would
love
say
the
that's
FSD
something.
example.
Yeah.
That's a great one. Mika.
So I'm going to pick something which is not robotics itself, but general intuition. Recently released a world model really for Rocket League, which is a game where cars play soccer. It's kind of a funny game. What's amazing about that breakthrough, which I think is about 2 weeks old or so, was that this world model could render consistently 4 different player views in that world, right? So traditionally, world models are sort of like, it's me with the world, my actions in the world, and that sort of unlocks sort of a multi-agent, kind of multiplayer, potentially interaction of multiple humans in the world kind of future, which I think is actually very important, because we often think in robotics purely about the task performance, lifting a cup, screwing something. But the world is full of other agents. It's full of things, people or AIs that we'll have to interact with. And so I think I didn't actually think it's going to happen so soon. I was thinking more like 6 to 12 months out that this is going to happen. But I think that's like a major stepping stone in the right direction.
That's a great example. Sergey.
I have an example where there's kind of a moral to the story. So a while back, there was this video that kind of went viral of the Boston Dynamics humanoid Atlas doing a backflip. And it kind of went viral because it was around the same time where there was a lot of, this was around CES, so there were a lot of demos of humanoids. And people were making fun of this because it does this backflip, and it doesn't quite stick the landing, and it sort of freaks out and does this like really weird, unnatural motion, but then stays upright. And people were saying like, oh, like, you know, Boston Dynamics is having all these problems. Look at all the Unitary robots doing these perfect backflips. But the folks that work on robots looked at this and they realized that actually the Boston Dynamics video is way more impressive because it actually doesn't fall. Like it freaks out, something really horrible happens and it stays upright. Then you remember this is a 170 kilogram robot. It's way heavier, way more complex than the more lightweight Unitary robots. And I think the lesson there is that, well, besides that Boston Dynamics has great controls engineers, is that with robots, the demo is never quite what meets the eye, right? The challenge is often not the things that you see in the demo reel, it's the degree of generalization, the ability of the system to handle unfamiliar situations and failures, and also all the complexity behind it. So it's often easy to be misled by the demo and not realize what are the really challenging problems there are.
Spoken truly like a person solving real-world use cases. I love it. Wei.
Yeah, I would like to echo Jim for the Tesla FSD, which is also taking over like most of my daily mileage. And actually, there is an even more impressive thing that I saw. For that company, I cannot disclose the name because I was on the R&D car of that. But that company can achieve similar kind of level performance in super crowded kind of street with a lot of like pedestrian, cyclists, or other kind of challenging situations for 1 hour without any intervention from the driver side. While the onboard compute of that car is only 1/7 of the Tesla like hardware 4 kind of compute, and with like even simpler kind of sensor suite on the vehicle. And for the robotics side, I think one interesting thing I saw in the ICRA and the CPR booth this year is a Chinese startup called Sudo, which is also trying to push the boundary for how to utilize the synthetic data. It's doing a lot of like generalizable kind of pick and place tasks with relatively zero shot kind of thing. Just let the audiences throw arbitrary things onto the table and do that.
Right. We're almost out of time. I have to ask this one question. The answer has to be a number, so we don't have time for anything else. A big movement in LLMs was what we call the Claude Code moment, and in the sense that that was the first use case where commercial takeoff of these technologies happened. In robotics, we think of the ChatGPT moment. I want to define this next one after that, the Claude Code moment, when the first commercial use case really takes off, just rockets off. And so your assessment, we'll start this time with you, Wei. Your assessment of what year does the first true commercially viable use case just takes off in the wild? And then if you have an idea for what that use case is, just a word or two on the use case as well.
Wow, that's pretty challenging. I will just try my best to give the number. So my guess would be around 3 years. So one thing is that we may also expect the data modality to be somehow fulfilled. Not just for example, a lot of egocentric or third-person view kind of large-scale data, but also the necessary physics modalities that can be well-grounded and associated with that. So those kind of data accumulation will take some time, and that could be one of the gain for having such kind of capability for the robotic foundation model.
Perfect. 3 years. Sergey.
I promise I picked this number before you answered, but my answer is also 3 years.
Okay.
I picked it in advance, though, so good check. But I actually don't know the area, and I think that the key here is to have models that are sufficiently general to radically lower the barrier to exploring different applications so that the community collectively can get through as many different possibilities as possible to arrive at that solution. So I think the key there is a general model so we can explore lots of applications.
That's a great point. 3 years. 3 years. Mika.
I'm going to say 3 years too. No.
Oh, come on.
No, I'll say 2. And I think the area is going to be somewhere in an industrial area because of a semi-structured domain, possibly availability of data. Yeah. Could be warehousing, could be manufacturing, right? So I actually think that the technology is sort of there. It's more of a question of finding the right economics, data inputs, and environments where you can actually deploy, which is where I think, for instance, deploying large robots in the home in terms of safety issues is probably further out. Right. So I think these semi-structured environments where you can tailor the use case, bring in general models, but also combine them with training on site or training in simulation. I think that's going to be a key.
Great. 2 years to the billion-dollar moment. Jim.
Earliest 2030, and we'll have more robots than iPhones 2035, and we're going to solve all robotics, everything, personal robot, industrial robot, no later than 2040.
Amazing. Amazing. Anastasis, bring us home.
Yeah.
Are we going to go longer than 4 or less than 2? Those are the bounds right now.
I think there's a wide uncertainty bar when it comes to deploying robotics for household tasks. I think I agree with Michael in terms of for very narrow enterprise use cases in things like logistics or in kind of the factory. You're gonna see deployment within the next kind of 2 or 3 years. But when it comes to actually dealing with the complexity of a home and being able to operate autonomously at many nines of reliability, it's gonna, I think, probably 5 to 10 years seems more likely.
Can I give an upper bound? I
Okay.
think for some economies, and this is not a technical argument, but we're going to have to solve it in 10 years. So if you take large Japanese corporations, for instance, in manufacturing, any industry, 60% of the workforce is 50 years or older. And so in 10 years, they will all be gone.
So those are the bounds, 2 to
So
10.
we'll
That's
have
the
to solve
deadline.
it by then.
All right. All of you are at the top of your domain, top of your fields. I really appreciate you spending your Saturday afternoon with us. Thank you so much for the wonderful presentations and the chat.